Hello. So, good afternoon, everyone. My name is Aditya Terkar, and today I'll be showing you a graphic user interface based construction for different types of windows. For finding, basically, we are looking at different window designs that are present in digital filters, and so I'll show you how they are constructed in this case. Okay, so basically, so let me tell you how many different types of windows. All right, just wait. Okay, here's so okay, so we have in my case I have discussed 1 2 3 4 5. So in my case I have discussed about 5 window types: rectangle, triangle, Hanning, Hamming, and Blackman windows. Basically these are the filters used. These are the windows that are used along with the digital filters to to have different possible advantages and disadvantages when it comes to the passband ripple, the stop band ripple, the transition width, and so on. Let me tell you what briefly a rectangular window is. Okay, so a rectangular window is one in which all the coefficients are 1, while a triangular window is something in which the ends of the window are tapered down to 0, while the middle value is the highest. The transitions from the lowest value to the highest value are linear. Hanning, Hamming, and Blackman windows are basically cosine based functions, so that their plots really appear like cosine curves, sinusoidally varying cosine curves. So it's hard to visualize within 9 coefficients, but when you place around 30 coefficients you can realize a bell shaped curve. So this is for Hanning. Hamming has slight offset at its ends. Blackman window on the other hand has more tapering at the ends of its values. Okay, so each of these windows have their own magnitude spectrum that you can calculate, and that is what is basically plotted over here. And there are certain calculations on main lobe, side lobe, main lobe width, transition width. So let me first briefly explain how the GUI is being constructed. We'll go then to the construction of windows. Okay, so constructing a GUI in MATLAB is very simple. All you have to do is type GUIDE in a command window. You should be able to open basically a new GUI, so that it will give you a platform where you can drag and drop all these fields, push button, slide options, static text, and all, so that you can create a basic layout like this. And then to achieve the functionality you use callback functions. Okay, so in this case the ones you see, choose window, length, main lobe, dB, and all these fields are basically static texts. They are not editable by the user, they just appear into your GUI or the interface. The white edit texts, the integer, dB, and radians, these are basically edit text boxes into which the user can write the data, as well as while running the program, if you calculate any value, that can also be shown on as an output in these fields. Okay, this rectangle basically, it's a pop-up menu, so that it provides all options to the users. The way you write down options into it is just by clicking into its properties and editing its string properties, writing down all the options here as I have listed here. So that way you can provide all options to the users. Now these two, the DTS plot and spectrum, are basically axes that you drag and drop over here and resize them, so that you can provide the functionality of plotting. Finally, the calculate button is nothing but a push button. So whenever the user pushes it, some action has to be performed. Now the way you control the GUI or let the interface work properly is that go to the calculate function, calculate this block's callback function. Okay, so this is the callback function of our CALC block. One thing one must remember, that each of those fields have tag values in them, and if you want to access any of those any of the members, all you have to do is use handles dot the tag value. Okay, so what we need to do in this case here is that whenever user presses the calculate button, we need to first fetch our input values, which is going to be basically the value that is stored in the pop-up menu, basically the filter. Basically we are trying to mean here the window type. That is done using the get function, get handles dot win menu. Now win menu is my tag that I have attached to this field, so that the values or the whatever text is stored inside it can be accessed. Now using this dash value, this single quote value allows you to map whatever is the window type there to numerical values. That is, the 1 corresponds to rectangular window, 2 corresponds to triangular window, 3 corresponds to Hanning window, and so on. Okay, now once we obtain using get handles, and basically string to double is required so that you get a numerical value, we calculate the discrete time sequence using individual functions. For rectangular window is nothing but simply a set of ones, so I have used MATLAB inbuilt function ones to define it, while for rest of the windows I have used triangular. I have defined separate functions. Triangular window, as we had seen, has 0 value at its end, while linearly rising till the middle value and then dropping down again finally at its other end. Hanning and Hamming window as well as Blackman window are basically cosine based functions. So let me show you what is an Hanning window. So in the Hanning window you can see the cos as a function of the iteration value in this case, which defines the discrete time sequence. Hamming window is very similar to the Hanning window, except that the coefficients are 0.46 and 0.54 instead of 0.5 and 0.5. Okay, similarly we also have Blackman window. Okay, just let me open it. Okay, so Blackman window uses three basically two cosine functions, one being double the frequency of other, and so the coefficients are assigned in such a way that you get very smooth tapering ends at the last values. Now having estimated this window sequence, the discrete time sequence, what we do is perform the frequency spectrum analysis. So for that, as these are digital filters whose frequency we in the digital domain restrict it from 0 to pi in my case for plotting and simplicity. The frequency, basically to calculate the spectrum, I have defined my own frequency resp function, which basically it takes in each and every frequency value defined in this lin space and calculates what is the magnitude, which is done by simple two for loops. Basically the outer for loop is for choosing with the frequency at which estimation has to happen, while the function here estimates your frequency values anyway. Okay, alright, so having done that, we plot the frequency spectrum here and also the discrete time sequence obtained. So to plot, we need to first access the graphical elements. So that is done using access handles.dts plot. The dts plot is the tag value of my GUI. So, and the same way we have handles.spectrum. Spectrum is the spectrum is my tag of this second graph element. So using them you can simply plot the values. So now comes the calculations for that. Please let me show you. So this main lobe dB. So main lobe dB basically tells you the attenuation that you get for the main lobe of your window. Then side lobe basically corresponds to the first peak value in terms of dB, and basically it computes the difference between the main lobe dB's for main lobe dB to that of the peak value, or to that of the side lobe part. The main lobe width is basically, just let me show you in this case. Okay, so let us see for a simple case of 9 coefficients. Okay, so the main lobe dB is basically this value at the peak one, which is around 12.1194. The side lobe dB is the peak value of the small side lobe, as I am encircling with my mouse pointer. Basically, it is the difference between this peak value to that of this side lobe's peak value over here. It basically tells the relative attenuation obtained. Now the main lobe width starts from this 0 value to that of the first minima. The transition width is basically the width between the width that you obtain from the main lobe width minus the 3 dB bandwidth of this spectrum. So when you calculate the difference, you get that way you can calculate. So in my case, I have written all MATLAB functions for them. So all this for, and by the way, you set the value, once you calculate, these are the calculating functions. Once you calculate, all you have to do is set handles the tag value, you edit the string property of it and write the value in there. Okay, so basically to find the peaks and the minima, you use find peaks function and minima find function. The find peaks function is an inbuilt function, while minima find is nothing. Minima find is a function that I have defined on my own. It basically calculates where the derivative is just crossing 0 and calculates the minima conditions for it. So all this, so it return basically local min is a collection. So basically local min is then the collection of points. All right, that way you can get the side lobe width. So let us once look at our entire working. So this is a Blackman window. Let us plot it for 13 value. So sorry, 19 values. So each filter has its own advantages and disadvantages. So starting from rectangle, as you can see, the rectangular window, the side lobe attenuation is not that high, and it is quite coming closer to the main lobe attenuation, which is a disadvantage. This disadvantage is around somehow the compensated in the other filters. The triangular filter, the triangle window has only one issue, that is the transition width, which is quite large value. Hanning and Hamming and all other windows are somewhat intermediate. You can see the changes in the number of lobes also as I change the filter. So these are all the different types of windows and their discrete type sequence as well as the magnitude spectrum. Thank you. So this was our today's experiment.